So this section is where we finally put together all the pieces that we've been dealing with and show you kind of how all of this works together between the finding the area and the antiderivatives that we've been looking at. So this fundamental theorem of calculus was established independently by both Newton and Leibniz. They were two mathematicians in very different parts of the world, and they kind of came to the same conclusion at the same time. So up until this point, researchers didn't know that the antiderivative and the integral, which is how we find the area under a curve if the curve is positive, they didn't even know they were related. So this was a big deal when this was discovered. So the informal statement says that differentiation and definite integration are inverse operations. So whereas the derivative calculates the slope of a tangent line and the integral calculates the area under a curve, and you can estimate the derivative using the slope of the secant line delta y over delta x. You can estimate the integral using the area of a rectangle delta y times delta x. So we've been using this same kind of curvy S symbol to represent anti-differentiation and definite integration if you give it bounds, whereas this one is a family of functions and this one is a number. Okay, and so the reason we use this S right here for integration is because Leibniz was calculating the integral as a sum. That's actually where the notation came from. So there was a big debate over who discovered it first, and now typically we credit both of the mathematicians, but the notation that we use is kind of a blend of the two. So this curvy S right here, Leibniz won that one. So this is a formal statement of the fundamental theorem of calculus. It says if a function f is continuous on the closed interval from a to b and capital F is an antiderivative of little f on that closed interval, then the integral from a to b of little f of x dx is equal to capital F of b minus capital F at a. So here's how we use it. Provided that you can find an antiderivative of little f, you now have a way to evaluate a definite integral without having to use the limit of a sum. So when applying the fundamental theorem of calculus, we usually use this notation. We evaluate the integral, and that's our capital F, and then we draw either a vertical line or a bracket with the bounds, and then we plug those in. So if I wanted to find the integral from 1 to 3 of x cubed dx, that would be x to the 4th over 4 from 1 to 3, and then we will plug the 3 in, so it would be 3 to the 4th over 4, and the 1 in, which is 1 to the 4th over 4, and then we can subtract those two numbers to get 20. Now, one thing that's important to note is that it's not necessary to include a constant of integration c in the antiderivative, because if you were to do that, you can see how c minus c, it would all just go away anyway. So we don't need the c anymore when we're doing definite integration, only when you're doing indefinite integration. So we'll do a couple of examples. If I want to find the integral from 3 to 5 of x squared minus 1 dx, I'm going to go ahead and evaluate the integral. So that would be x cubed over 3 minus x, and that's going to be my capital F of x right here. This is going to go from 3 to 5. So I'm going to have f of 5. I have f of 5, which is 5 cubed over 3 minus 5, minus f of 3, which is 3 cubed over 3 minus 3. So this is 125 over 3 minus 5, and this one is 9 minus 3. So that gives me 110 thirds minus 6, or 92 over 3. And this would be the value of the definite integral. So no sums, no limits, just take the antiderivative and then plug in the bounds. So let's do another one. I've got the integral from 4 to 9 of the square root of x dx. So I'm going to write this as the integral from 4 to 9 of x to the 1/2 with respect to x. So this will be x to the 3/2 divided by 3/2, all from 4 to 9, or 2/3 x to the 3/2 from 4 to 9. So this will be 2/3 times 9 to the 3/2 minus 2/3 times 4 to the 3/2, which ends up being 2/3. 9 to the 3/2 is going to give me, let's see, that'll be 27. And 4 to the 3/2 is going to give me 8. So this all subtracts to be 38 over 3. And that would be the value of my integral. Looking at this one, I'm going to have x to the 4th over 4 minus x squared over 2. And that's going to go from 2 to 4. So this will be, the first one will be 4 to the 4th over 4 minus 4 squared over 2. And the second one will be 2 to the 4th over 4 minus 2 squared over 2. So this is going to be 64 minus 8 minus 4 minus 2, or 56 minus 2, or 54. Now you do have to show your work. I at very least need to see you actually find the antiderivative, and it need to see somewhere along the line of you plugging this in before you give me the final answer. I know that you can calculate these on some calculators, but if you just give me an answer that's a number and you don't show any work, you will not get full credit. So just be warned. If we're trying to find the definite integral of an absolute value like this is 2x minus 2, absolute value from 0 to 3. It might not hurt to go ahead and talk about the absolute value of 2x minus 2, which would be 2x minus 2 if 2x minus 2 is greater than or equal to 0, and the negative of that if 2x minus 2 is less than 0. So that's 2x minus 2 if x is greater than or equal to 1 if you solve for this, and negative 2x plus 2 if x is less than 1. So we can approach this integral by breaking it up at 1. So I'd have the integral from 0 to 1 plus the integral from 1 to 3. And from 0 to 1, that's going to be the negative 2x plus 2. And from 1 to 3, that's going to be the 2x minus 2. So this integral on the left here, we're going to have, let's see, negative 2x squared over 2 plus 2x, and that's going to go from 0 to 1. And we can actually integrate this separately if you want to, so that's negative x squared plus 2x. So that would be, for the 1, we would have negative 1 squared, and the 2 got canceled there, so negative 1 squared times 2, or plus 2 times 1. And then for the 0, we would have negative 0 squared plus 2 times 0. So that's that one. And we'll keep going from here. So we would end up with, let's see, we would end up with negative 1 plus 2 minus 0, or just 1. The blue integral, we would have 2x squared over 2, so the 2's cancel, minus 2x. And that's going to go from 1 to 3. So that will be 3 squared minus 2 times 3 minus 1 squared minus 2 times 1, or that's going to be 9 minus 6 minus 1 minus 2. And this one ends up being 4. So when I add these together, I actually get 5 as my answer. Now, as long as the definite integral would represent the area of a region, or area of the space under a curve, okay, meaning as long as the function is positive on that whole interval, then we can use the fundamental theorem of calculus to find the area under a curve. So this example, we're going from x equals 0, so right here, to x equals 4. And you can see that on this whole space, the curve is positive. So we're looking for the area of this region right here. So the area would be the integral from 0 to 4 of the function, which is 3x squared minus 2x plus 5 with respect to x. So that's going to be 3x cubed over 3 minus 2x squared over 2 plus 5x. And that's going to go from 0 to 4, or just x cubed minus x squared plus 5x from 0 to 4, which is going to be, see, we'll have 4 cubed minus 4 squared plus 5 times 4 minus 0 cubed minus 0 squared plus 5 times 0, which is 64 minus 16 plus 20 minus 0, or 68, and this is area, so this will be units squared. So as long as you have a function that's positive on the whole interval, you can actually use this process just to find the area.